I'm the general manager for Amazon Neptune, our new graph database offering. I also run Amazon Elasticsearch Service and Amazon Cloud Search. And with me today is Brad Beebe, who is the head of product management for Amazon Neptune. Before we talk about Neptune and why graphs matter and why we actually went down the journey of building a graph database, I did want to tell you a bit about our philosophy around databases at AWS and what actually caused us to start working on this very purpose-built database. So purpose or matara, that is really kind of how we think about databases. We think about it as, the purpose is the reason for building something, or creating something that has a reason behind it. And at AWS, we believe that databases that are purpose-built for a very specific task are going to do better, are going to perform better, are going to be easier to use and scale better than general-purpose databases that are trying to solve every problem that's out there. So that is a very key fundamental belief in how we think about it. And our goal is really to deliver the best tools for the job to developers, whether that's languages, databases, or analytics engines. If you go back in time and think about the traditional applications we've built, CRMs, ERPs, HR applications, these applications have had hundreds of users, maybe thousands of users. We thought about data storage in gigabytes, and when they were really big, we thought about them in terabytes. Response times typically had to be in seconds, and at most, we'd had tens of thousands of concurrent requests per second, and usually much less than that. And in general, we would scale up the systems, and if the system was down for a bit, it wasn't such a big deal because the amount of users we had was very, very limited. In this era, we would basically very often use one database and just put everything in that one database, and it was good enough. And we didn't have the really difficult challenges we have today, where we have to build a whole different class of applications. So today, we're building cloud-scale applications. We definitely see a lot of them here in Israel, ad tech, security applications, very large applications reaching millions of users. We think of storage, like the small storage is usually terabytes. We're seeing petabyte applications. We even have some customers who have exabytes of data. These applications are global. The new second is millisecond from our perspective. And in the ad tech world, millisecond isn't fast enough, and you need microsecond latency. And so this starts to get us to think about, okay, when we have to move from these kind of old applications to the new ones, can we really achieve, these kind of goals with a one-size-fits-all strategy? Also, when we think about scaling, it's not just about scaling up. It also is, because we care about memory and we want to, have as much data and memory as possible. But we also think about scaling up, scaling down. And given that we're starting to use a lot of resources, being able to pay on a pay-as-you-go basis and not have to over-provision is also something that is extremely important to us. So basically, as we were thinking about these new applications, we really start to think about, what's driving those applications. It's much faster response times, much faster scale, and the use cases are starting to become very, very diverse. And so we've basically spent a lot of time at AWS to start to build databases that can meet very specific needs of yours to really build very innovative applications. And so let's talk about some of the some of the database paradigms you really care about. So I'll take e-commerce as an example, not because we're Amazon and we have Amazon.com, but it's just an example I like. If you think about the kind of data stores we use today and how that would relate to an e-commerce application, think about the relational model. Really good if you care about referential data, referential integrity, you care about transactions. It's really good in an e-commerce use case for the transactional processing side. So, when people say relational is dead, we think relational is great. We have offerings like Aurora on the relational side. But when you start to think about the shopping cart, now you have, hundreds of thousands or millions of users coming to your e-commerce website, and you need to have very, very fast response time, because if you lose them during the buying journey, they're never going to convert into the transaction. And so there you may have something more like a key value store. That's why we built Dynamo. Dynamo gives you single-digit millisecond response times, pretty much infinite scale, and super useful for kind of a shopping cart example. Think about document store. Dynamo also supports document. Obviously, other databases also have document capabilities. Documents would be really good for the product page, right? The product description, usually that's a more fluid kind of data that you want to keep. It's going to evolve quite a bit. It's not going to be super structured. Having a nice JSON-based document store is really exciting. And so talking about Graph, why do we build Graph? If you think about e-commerce and shopping, one of the key things you can do with Graph, and Brad's going to talk a lot more about how you can do that in Graph. What about a recommendation? If you know what people bought and you know who they like and what kind of products they like, what their interests are, who their friends are, you can actually start to understand from that connected data, you can start making recommendations and actually convert more customers on your websites to buying other products. And we'll give you an example later on that shows you exactly how you would actually think about that. And then last but not least, time series. Many of you probably know Elasticsearch. That's one example of an offering we have. But time series data is really growing. It's growing super fast, both because of IoT, application monitoring, and a lot of other use cases. So when we think about this again as AWS, our goal is really to deliver the best databases that around these different database characteristics. And sometimes it may be one database that can do both, or we will build very, very specific databases for that purpose. I've already mentioned quite a few of the databases, so I'll skip this slide. But basically, from relational to non-relational analytics engines, you have a lot of choice at AWS on what to use. So let's talk about Graph. What makes Graph really exciting and unique is Graph is actually less about the data, and it's more about the interconnection of the data. It's how does data relate to each other. And more and more of your data actually has these kind of connections within it, whether you notice it or not. And those interconnections can actually help you solve problems that you weren't able to solve previously. The problem we've had to date is that being able to solve those problems in traditional databases has been far too difficult, has been slow. And so building a purpose-built graph database can actually help you look at the data in a very, very different way and deliver experiences and capabilities in your applications that are very differentiated compared to the kind of applications that you've built before. What we see very often is that many people actually know they have graph problems, but because they haven't been very good graph tools, they either haven't solved them, or they've used databases like Dynamo or relational database to try and kind of solve a graphish problem. But the key issue is always, but then you start to really fall down on things like performance and agility and so on. So I'm going to hand it over to Brad now. Brad is an expert in graph. He's been in the graph space for many years, and he'll take you much deeper into what kind of graph problems are out there, how you should think about solving them, and then talk very specifically about Neptune and what some of the capabilities are in Neptune.
Thank you. So before we get started, I wanted to just see from the audience, how many people have used a graph database before? Okay, a couple. How many people have used Apache Tinkerpop or the Gremlin language for imperative traversals? A few less, that's great. And any RDF Sparkle users, Resource Description Framework? Okay, great, fantastic. Well, one of the things that personally I like about being in the graph space is really the huge range of use cases that you get to experience. And Andy talked about purpose-built databases, and what we really saw was that increasingly our customers needed to process data that was both rich and highly connected. And it was rich in that it had a diversity of different data types, different schemas, different sources. It came in at different rates from different sensors. And most importantly, what sort of linked all of these different use cases and customer needs together was that the real core value in the applications was in processing the relationships that the data created. And so these are really the 6 use cases we're really focusing on for Amazon Neptune. The first is social networking. Social networks are really all about people, people's interactions, things that people like, ways that they express actions that they do. And so social networks are a classic graph application. The second major area are different types of recommendation systems. So things ranging from product recommendations to friendship recommendations to other applications. Knowledge graphs are an area we've seen a lot of growth in the past 12 to 18 months. Knowledge graphs use a graph model to represent domain information, and then they enable you to do things like improve information retrieval or help customers answer new questions by really understanding the core concepts that they're asking. Fraud is a very traditional graph application. We see both real-time fraud use cases where people want to try and evaluate in a transaction timeline whether there may be fraudulent activity. And then we also see retrospective use cases where people want to look longitudinally at a set of transactions over time and try and understand what patterns may be in there and see if they can learn to prevent future fraud. The life sciences has a long history of investing in high-quality data to model things like proteins, chemical compounds, so on and so forth. And so there's a number of different applications in life sciences ranging from drug hypothesis regeneration, where you look at existing improved drugs and you look at the protein receptors and try and understand if there's new treatments that they can be applied to using research and information retrieval techniques where you provide very fine-grained topical information on research and then allow people to retrieve it very quickly, to all the way to just using graph-based data integration techniques where you take information coming out of different medical systems and try and combine it for a fused view. And then really lastly, networks themselves are fundamentally connected data structures. And so we see network use cases ranging from protecting the boundary, how can I know what's happening at the edge of my network, to capacity planning, what will happen if this particular node goes down. And so there's just really a breadth of use cases. But let's look at a couple of more detailed examples. So this graph is showing sort of a hypothetical. On your right, we see social information. On the top, we have some product purchase history. On the bottom, we have some shared interest. And by looking at features of the graph and trying to complete them, we can use this as the basis for making recommendations. So for example, by looking at shared interest and purchase history, we can make a product recommendation that people who also followed sports purchase this product. We can do the same kinds of things in a social context. So by noticing that there's a shared friendship here, we can recommend a relationship to say, here's someone that you may also know. I mentioned knowledge graph applications earlier. This particular example is taken from the W3C's Knowledge Graph Primer. And on the right, you see some information about art, artwork, the artist, where it's located. We've also overlaid a social graph, some travel history. And by combining all of these things together, we can start to build applications that answer questions like, who painted the Mona Lisa? What museum should Alice visit while she's in Paris? Or what artists have paintings in the Louvre? Thomson Reuters is one of our public preview customers for Amazon Neptune, and they have quite an interesting use case. What they're doing is they are using a graph model to model tax policies in various different geographic regions. And then they also model their clients' corporate structures, and they use the combination of information to help their customers understand what are my tax compliance obligations in all of the places where I do business, and beyond that, also helping them to optimize their tax exposure and suggest different strategies that may help them, as they look at their liabilities. So in thinking about the product, we sort of asked ourselves, well, what can customers use to process this kind of data. And the first thing that came to mind was, how about a relational database? Can I use a relational database to process graph data? And the answer is yes, of course you can. But there's a couple of things that you need to be aware of. The first is that the query language for a relational database is SQL. The construct that you would use to traverse a graph or to express graph queries is a join operation. And graph applications have a very large amount of join operations, and so SQL queries to express graph traversals very quickly get complicated and expensive to execute. And this is because the second point, which is that relational database management systems have a very different type of workload than you see in graphs. Graphs are characterized by a large number of self-join operations, and so the kinds of I/O characteristics that relational systems are designed to handle are very different than graphs. So you get these large numbers of joins executed over relational systems, and what you see is a decline in query performance and an increase in query complexity. And then the last thing that we noticed was that one of the key features of graph and why customers wanted to use it was that they could very easily combine data that they really didn't even think about in their design about bringing it together. So the flexibility of the graph. In relational databases, it can be hard to evolve the schema quickly. Let's look at it from a slightly different concept here. Here on your left-hand side, you're seeing a very basic entity relationship diagram of a hypothetical HR system. And this was an application that was built specifically to handle HR, and it does that very, very well. But there's a lot of different information in it. And so if you want to start to ask questions of this information that's really outside of the scope of what the application was built for, it becomes very difficult. Now, if you look on the right-hand side, you'll see the same kinds of information, but represented in a graph. And what you'll notice right away is that rather than being buried in foreign key relationships, like in the ER diagram, the relationships themselves are first-class objects in the data model. And so if you want to ask questions like, what are the skills required to build a particular product, it's very easy and straightforward to do that, whereas that information is buried within the relational system. So what's a graph database? Well, a graph database is a database system that's optimized for handling graph workloads, and it provides support for query languages that are designed to very efficiently and concisely express graph operations, traversals, and graph patterns. There's two leading models for graph. The first is something called property graphs. Property graphs have nodes and edges have attributes. The leading framework for a property graph is something called Apache Tinkerpop, which is an open source project, and it provides a language called Gremlin, which allows you to write imperative traversals over property graphs. The second major graph model is something that's called the Resource Description Framework, or RDF, which is a standard from the World Wide Web Consortium, and it has an associated query language, which is called Sparkle, which provides a declarative graph query language for RDF graphs. Now, there are some differences around the edges of the models, but in general, you can do almost any application with either model. What we tend to find is that customers who are coming from a relational database background often find property graph a very, very natural transition. So if you're used to thinking of things in tables and rows, then thinking about things with nodes and node properties and edge properties can be a very natural transition. Also, the Gremlin language, with its imperative model, makes it very easy to think about applications where, in building the application itself, users interact with it, and they're effectively building graph traversals, sort of imperatively as they interact with their application. So if you think about a social app, as you expand out a hop, you're really building an imperative traversal. On the other hand, customers like RDF graphs because RDF gives you an exchange standard. And so there's a large number of different data sets that are publicly available. Some of them are published by government organizations, research organizations, commercials organizations. And these kinds of data sets, things like Wikidata, things like PubChem, things like ChemBL, they allow you to rapidly bootstrap applications. So if you have an application that wants to take advantage of these data sets, RDF can be a very good choice. Also, if your applications themselves are producing information content that you'd like to have other people consume, the Exchange standard gives you a benefit for being able to publish and distribute the information. So let's look at a hypothetical example here. On your right-hand side, we have a picture of a graph data model. And this data model is describing a university structure. And so we have a university. Universities have departments. Departments have professors and graduate students who teach courses, and there's students, and students take courses. Students and professors receive degrees from different universities. There's sort of a snapshot here, which is looking at the class hierarchy of professors. And so this is sort of the data model that we're going to use for our example. Now, we want to ask a question here. And the question we want to ask is a graph pattern. So we want to say, find all the graduate students who received an undergraduate degree from the same university. And to answer this, we're going to construct a graph pattern. So we're going to first look for graduate students that are members of a department, where that department is in a part of a university, and they also receive their undergraduate degree. Now, for folks who are familiar in the graph space, this example is taken from a fairly well-known graph benchmark. And so now let's look at how this looks in the various different graph models. So this is looking at some representative input data. This is in the format for our property graph, the Neptune property graph. And at the top, you'll see various different information about the nodes. And so this is a CSV format. The ID is shown on the left-hand side. The label, which in a property graph is very much like a type. And then you can see that there's attributes. So this should look very familiar for anyone that's worked with CSVs or relational databases. On the bottom, you'll see an example of some input data for the relationships or the edges. There's an ID for the edge, then a from and to, and then a label. The label, again, is a basic typing mechanism. And so this is the example of the input data. And we're going to ask this question, and we're going to express it as a Gremlin imperative traversal. So the first thing that we're going to do is we're going to find all of the graduate students. And we're going to save that off as a variable that we're going to use later. Then we're going to traverse out one hop and say, where did this graduate students get their degree from? Then we're going to look for incoming edges to find departments that are part of these universities where they got their degree. Then we're going to find incoming edges where the graduate students are actually members of that department. And we're going to join that effectively with the starting point of students. So we're going to take the intersection of those graduate students that received the degree from the university with those that are a member. And that's how we're going to answer that question in Gremlin. Now, this is a snippet of data that would effectively match that Gremlin traversal. And so we can see graduate student, the relationship type or the type at the top there. We can see the department that they're a member of. We can see the edge relationships there and their undergraduate degree. And so that's an example of how that traversal would match for a property graph. Now let's look at the RDF data model. So RDF, or the Resource Description Framework, was originally designed to describe resources that are available on the web. And as part of that, it makes extensive use of something that they call an IRI, or an Internationalized Resource Identifier. So this is essentially like a URL, and that allows you to distinctly and uniquely express the concepts of identity in RDF. And so RDF consists of different, what they call triples. Each triple has 3 parts, a subject, a predicate, and an object. And so at the top we can see these first 2 lines define types. So this graduate student has a type of graduate student. Then they have some property values, name, some relationships, the member of, and then some other data associated with it. Whereas Gremlin provides an imperative traversal model, Sparkle provides a declarative graph query. And so this is the Sparkle query that asks the same question. So the first 3 triple patterns here, and Sparkle queries are expressed as triple patterns. Find me all of the students that have a type graduate student and store it in this variable, which is conveniently called student. And then we have a similar type of triple pattern for universities. Find me all the universities, then find me all the departments. And now we start to express our graph pattern. And so of these students, universities, and departments, find me the students that are a member of these particular departments, where the department's part of the university, and the student has an undergraduate degree from that department. And what you'll see is that in a Sparkle query, the use of these shared variables effectively creates the join patterns that you need to use to evaluate over the graph. And so let's take a look at what the data would look like that would match this Sparkle query. So here, you'll recall, this was the data we showed earlier, and then we highlighted the triples that would be evaluated to match that Sparkle query. So we can see we found this graduate student based on the type. We found that they're part of the university. We found where they got their undergraduate degree from. And then we have the information that completes the relationship between the university and the department. So this is an example of the same question expressed in the RDF and Sparkle model. So graph is very complementary to other different analytic techniques as well. For anyone that was in the Innovate track, they saw Yuri's talk perhaps on sort of serverless with using recognition. This is sort of a similar example using Amazon Comprehend. Here what we're showing is the end result of a workflow that takes RSS feeds, so news information, processes them with Amazon Comprehend, extracting the named entities, so persons, places, and things, transits them through S3 for storage, then loads them into Neptune itself, and then has an open source graph visualization on top where we can see the different types of information that's being displayed by different organizations. So this is an example of the kinds of things that you can do with a graph where you're taking information generated from other systems that provides relationships. You're using the graph to integrate it together and to drive either visualizations or other analytic capabilities. So graphs seem pretty cool, right? Maybe? Not as cool as the music that came earlier? So we wanted to look at, so graph database is a good thing. What are the alternatives for customers to use a graph database? And so we looked around, and a couple of things really struck out to us. One was that we talked to a lot of customers who had some success with the proof of concept with the graph database. So they tried some small scale application, they had built it, it had worked great, they really liked it, they found it easy to use, and then they went to take it into production. And they had a couple of challenges. The first of which was that as they increased from a POC data scale into that of production, they saw a rapid decline in query performance. The second was that when they needed to move beyond just a single open source or community edition and put things into production where they needed to have high availability, read replication, security features, encryption at rest, what they found is that these kinds of features were either not available in open source or community editions, or very, very expensive to license in enterprise editions of these products. The second thing that we found was that while some alternatives provide support for both graph models, there tend to be a very strong bias towards one or the other. So for your property graph applications, if you chose an alternative that supported both property graph and RDF, you get very good performance potentially for property graph, but not so good for RDF, and vice versa. So this was the overall context for which we designed Amazon Neptune. So Amazon Neptune is designed to be an interactive graph database that supports graph applications that need very high throughput query answering with low latency. And in particular, we think about graph query operations in two different categories. The first are OLTP-like graph queries, which we define as parameterized graph traversals of less than 3 hops or parameterized graph patterns. And for these kinds of OLTP-style reads, the target throughput is to support up to 10,000 OLTP reads per server per second with a latency of less than 50 milliseconds. And we support horizontal read scaling of up to 15 different read replicas, so you can scale that OLTP throughput up to 150,000 queries per second per cluster. The second kind of read that we think about are OLAP-style queries. And we think about these as traversals of 3 or more hops, on-bound graph patterns, complex filters, combinations of all 3 of these things. And for OLAP-style queries, the target throughput is to support up to 100 OLAP queries per server per second, with latency targets that vary. And they vary from hundreds of milliseconds all the way up to minutes, because the ability to effectively evaluate OLAP queries very much depends on the shape of the data that you have underneath of it. The second thing that we really tried to focus on with Neptune is for it to really be an enterprise-ready, fully managed graph database experience. So at all levels, regardless of the instance size that you choose to use with Amazon Neptune, you can configure it with multi-availability zone, high availability. You can configure it with encryption at rest using customer-managed, i.e. KMS keys. You can configure up to 15 different read replicas. And you can do that all through the console, SDK, or API. So we wanted to make that a very, very easy experience for you. Also with Neptune, you don't have to do things like configure specific indices over different properties if you want to query them. These kinds of things we do for you and provide you a very good query experience without having to do a large amount of operational maintenance. And the last key feature for Neptune is that for Neptune, both property graph and RDF are really first-class data models that we're supporting. And we provide an optimized query experience for both. So you can choose the data model or API that's best suited for your application. And we talk to a lot of customers that have use cases for both in the single organization. So this is a high-level view of the Neptune architecture. Across the top, you'll see the different use cases that we're supporting, the graph-focused APIs. And then the blue box in the middle is really the core of Neptune. Neptune is a purpose-built graph database engine that's durable and ACID with immediate consistency. It's built on a cloud-native storage layer that's shared with other database services technology. And that's what enables us to offer the HA, the read replication, encryption at rest. In addition to that, we also provide a REST API for you to do fast parallel bulk loads of graph data that you have stored in S3 buckets into Neptune. And for property graph, we support a CSV-based graph serialization, which you guys saw an example of earlier, where you take nodes and node properties and serialize them in CSV files, and you take edge and edge properties and serialize them in CSV files. For the RDF data model, we support 4 different serializations in the bulk loading capability, something called Turtle, N-triples, N-quads, and RDF XML. So just as a quick summary of the fully managed aspects of Neptune, we can see that it's completely operable via console APIs and SDKs, provides multiple AZ high availability, read replication, encryption at rest, encryption in transit, and backup, restore, point-in-time recovery. All of these are easily done through the management console. Neptune supports VPC deployment. When you provision an instance of Amazon Neptune within your VPC, you get 3 different things that show up. You get a network interface that provides a Tinkerpop WebSocket server with which you can use to connect your Apache Tinkerpop clients. We support Apache Tinkerpop 3.30 currently. You get a network interface that provides a REST endpoint that implements the Sparkle Protocol 1.1 with which you can use to connect your RDF Sparkle clients. And then, of course, you get a REST interface for that bulk loading capability where you can post JSON documents that describe specific bulk loads in terms of the S3 bucket, the IAM credentials you'd like to use, and various parameters. The underlying cloud storage layer provides the read replication and also provides the underlying data protection. And so within the data, within this cloud native storage layer, each piece of your data is replicated 6 times across 3 availability zones with a quorum of 4 of 6. And this allows us to provide very, very low latency read replication, typically less than 10 milliseconds. We have repeatable reads on the read replicas, and we have immediate consistency on the write master. So I talked a little bit about Thomson Reuters. These are some other customers that are previewing Neptune. We did a reInvent talk this year with Siemens. Siemens has a number of different graph use cases. The ones we talked about this at reInvent, we're using modeling industrial designs as graph, integrating that with various support costs, and then using the resulting knowledge graph to help them to estimate the how to bid and price support contracts. AstraZeneca is a life sciences firm. They have graph use cases ranging from drug discovery to research information. FINRA is the US Financial Regulatory Agency. They're analyzing various different stock and equity transactions from the context of making sure that they comply with various regulatory requirements, and of course Amazon Alexa as well. So Neptune is in preview now. It was announced at the reInvent conference in November. You can sign up by visiting the product page and providing your AWS account ID and requesting access, and we'd love to have you try it out. We're planning to take Neptune into general availability later this year. The preview is only in one region. It's in the US East Northern Virginia region. At GA, we plan to expand into 3 additional regions, so we'll support US East Ohio, US West Oregon, and then EU West Dublin. The feature set is largely what's available in the preview, plus we're adding IAM-based authentication for access to the Gremlin WebSocket server, the Sparkle Protocol 1.1 REST endpoint, and the bulk loader. And we've already rolled out the assumed roles bulk loading into the preview currently. So thank you very much, and we'd love to have you try out Neptune. Thank you.